The history of the Second World War is frequently presented as a clash of massive numbers, a simple ledger where victory is decided by the sheer volume of steel melted, coal mined, and airframes stamped out of industrial assembly lines. We are told of the thousands of Soviet tanks rolling off the lines at Tankergrad, or the endless waves of fighter aircraft emerging from factories nestled behind the Ural Mountains. Yet this traditional narrative harbors a profound metallurgical and chemical illusion. Beneath the surface of these grand strategic statistics lies a microscopic world where the laws of organic chemistry and thermodynamics dictate the limits of military power. In the high-altitude air battles of the Eastern Front, the ultimate arbiter of performance was not the thickness of armor or the caliber of cannons, but rather the molecular composition of a single liquid, which was aviation gasoline. Every engine, no matter how masterfully designed, is ultimately a mechanical converter of chemical energy, and its performance is strictly bound by the purity and octane rating of the fuel that feeds its combustion chambers. To understand the absolute bottleneck that aviation gasoline represented, one must examine the hostile physics of high-performance piston engines. As aircraft engines climbed into the thinner air of the upper atmosphere, they required superchargers to mechanically compress the intake air, forcing a dense charge of oxygen into the cylinders to maintain power. However, compressing this air-fuel mixture also drastically increased its temperature and pressure inside the cylinder. Under these extreme conditions, standard petroleum fuels of low molecular stability would undergo premature self-ignition, a catastrophic phenomenon known as engine knocking or detonation. Instead of a smooth, controlled flame front propagating across the cylinder, the fuel would explode violently and unpredictably. This detonation created localized shockwaves and extreme thermal spikes that would literally burn holes through steel pistons, snap connecting rods, and melt spark plugs within seconds. To prevent this destructive self-ignition, engines required fuels with high octane ratings, which measure a fuel's resistance to premature detonation. High-octane fuels, particularly those rated at 100 octane or higher, allowed engine designers to increase compression ratios and boost pressures, squeezing hundreds of additional horsepower from the same engine block without risking self-destruction. In 1941, as the German Wehrmacht launched Operation Barbarossa, the Soviet Union possessed one of the largest air forces in the world, yet its entire aviation infrastructure was built upon a chemical foundation of sand. The vast Soviet oil fields in Baku, Grozny, and Maikop produced immense quantities of crude, but the domestic refining industry was structurally incapable of producing high-octane aviation fuels. Soviet refining technology, largely dominated by thermal cracking rather than advanced catalytic cracking, was optimized to produce low-octane, low-purity, agricultural-grade gasoline, typically ranging from 66 to 74 octane. This low-grade fuel was perfectly adequate for agricultural tractors, river barges, and slow-moving trucks, but it was a death sentence for high-performance military aviation. The primary Soviet domestic aviation fuel was B-78, which had an octane rating of only 78, occasionally boosted to 95 through the dangerous addition of excessive quantities of tetraethyl lead. This lead additive, while artificially elevating the octane rating, left heavy lead deposits on spark plugs and valves, leading to frequent engine misfires and severe spark plug fouling that required constant maintenance in the freezing conditions of the Russian front. Soviet aircraft engines, such as the Klimov M105 and the Mikulin AM-38, were forced to operate under severely restricted supercharger boost limits, preventing them from achieving their true aerodynamic potential and leaving Soviet pilots at a massive permanent tactical disadvantage in the skies. This chemical deficit was severely compounded by a simultaneous metallurgical disaster that struck the Soviet Union in the opening months of the German invasion. Before the war, the primary material for high-performance military aviation was duralumin, a light, strong aluminum alloy that allowed for thin-skinned, aerodynamically efficient airframe designs. However, the rapid advance of the German Wehrmacht in the summer and autumn of 1941 completely shattered the Soviet aluminum industry. The massive Dnieper aluminum smelter at Zaporozhye was sabotaged and abandoned, while the Volkhov plant near Leningrad was cut off by the German blockade. In an instant, the Soviet Union lost over 60% of its primary aluminum smelting capacity. With duralumin reserves rapidly dwindling and the remaining smelting facilities relocated to the Urals still years away from reaching full capacity, Soviet aviation designers were forced to find an immediate, desperate alternative. The solution lay in the vast ancient forests of Russia. Under the direction of talented engineers such as Alexander Yakovlev and Semyon Lavochkin, the Soviet aviation industry turned to a specialized material known as delta wood. Delta wood consisted of thin birch veneers impregnated with phenol formaldehyde resin, a type of early plastic known as bakelite, which was then compressed under immense heat and pressure. The resulting material was remarkably strong, resistant to rot, and relatively easy to work with using semi-skilled labor. Fighters like the early Yakovlev Yak-1, Yak-7, and the Semyon Lavochkin LaGG-3 were constructed almost entirely of wood, with wooden wing spars, plywood skins, and only minimal metal reinforcement in high-stress areas. While delta wood was a triumph of emergency wartime engineering, it carried a severe physical penalty. Wood has a much lower strength-to-weight ratio than duralumin, which meant that to achieve the same structural strength, wooden spars and skins had to be significantly thicker and heavier than their metal counterparts. A wooden wing was bulky, aerodynamically thick, and added hundreds of kilograms of dead weight to the aircraft airframe. This structural weight penalty created a devastating double handicap when coupled with the fuel crisis. Because Soviet engines were forced to run on low-octane domestic fuel, they could not generate the high horsepower required to overcome this massive weight disadvantage. A wooden fighter powered by an engine with restricted supercharger boost was a heavy, sluggish machine. The early Lavochkin LaGG-3, nicknamed by Soviet pilots as the varnished guaranteed coffin, suffered from a terrible power-to-weight ratio. It was slow to climb, slow to accelerate, and bled energy rapidly in tight turns. German pilots flying the light, all-metal Messerschmitt Bf-109, which ran on premium 87 or 96 octane synthetic aviation fuel, could easily outclimb, outrun, and outmaneuver their heavy wooden Soviet opponents at almost any altitude. The Soviet Air Force was trapped in a vicious cycle. Their aircraft were too heavy because they were made of wood, and they could not climb or fight effectively because their engines lacked the high-octane fuel required to generate the necessary horsepower to pull that extra weight through the air. The salvation of the Soviet Air Force would not emerge from the timber yards of the Urals, but from the highly advanced catalytic cracking towers of Texas, Louisiana, and New Jersey. Through the mechanism of the Lend-Lease Act, the United States embarked on a massive, unprecedented effort to transfer its cutting-edge chemical and petroleum technology to the struggling Soviet state. Between 1941 and 1945, the Allies shipped an astronomical 1,500,000 metric tons of premium high-octane aviation fuel and critical blending agents to the Soviet Union. This immense volume of fuel flowed through three main logistical veins: the perilous Arctic convoys to Murmansk and Arkhangelsk, the vast Persian corridor winding through Iran and across the Caucasus Mountains, and the long Pacific route ending in Vladivostok. Every route was a monument to logistical determination, where merchant mariners braved German U-boats, Luftwaffe bombers, and freezing Arctic conditions to deliver the precious liquid cargo that would keep the Red Army's wings aloft. Yet the raw tonnage of imported fuel only tells a fraction of the story. The true hidden genius of the American petroleum pipeline lay in the transfer of high-purity chemical components known as alkylates. Alkylates are highly stable, synthesized petroleum elements such as iso-octane that possess an exceptionally high octane rating of over 100. Because these blending stocks were incredibly pure, they could be mixed with low-octane base gasolines to drastically elevate their overall performance. The Soviet Union, while having abundant crude oil in Baku and Grozny, lacked the advanced chemical refining plants to produce alkylates domestically. Recognizing this strategic bottleneck, the United States did not just ship finished aviation fuel, they shipped over 300,000 tons of pure alkylates and essential additive packages, including tetraethyl lead and isopentane. Soviet chemists blended these high-potency imports directly into their low-grade domestic refinery runs. This chemical compounding allowed the Soviets to turn millions of tons of low-grade domestic gasoline into high-performance aviation fuel, multiplying the practical impact of every single gallon of American alkylate by up to 5 times and transforming their entire domestic refining industry overnight. This chemical transfusion had an immediate and revolutionary impact on Soviet engine performance. Armed with high-octane fuel and alkylates, Soviet engineers could finally unleash the latent power of their aircraft engines. The Klimov M105PF engine, which powered the vast majority of Yakovlev fighters, was modified to accept higher supercharger boost pressures, increasing its output from 1,100 to over 1,260 horsepower. This extra power directly translated into increased speed, a faster rate of climb, and superior acceleration, allowing Soviet wooden fighters to finally meet the Luftwaffe on equal aerodynamic terms. The chemical genius of American refineries had effectively neutralized the weight penalty of Soviet wooden aircraft construction. A Yak-9 fighter running on high-octane blend was no longer a sluggish, vulnerable target. It was a fast, lethal interceptor that could hold its own against the best fighters Germany could put in the air, proving that the chemical formula of fuel was just as critical to air combat as the aerodynamic design of the airframe itself. The strategic value of this high-octane fuel became even more pronounced when examining the performance of the direct military hardware shipped from Western factories to Soviet airfields. Under Lend-Lease, the Allies delivered over 18,000 combat aircraft to the Soviet Union, including thousands of Bell P-39 Airacobras, Curtiss P-40 Warhawks, Hawker Hurricanes, and Supermarine Spitfires. These aircraft were engineered to the exacting high-altitude performance standards of the Western Air War, which meant they were built specifically to run on premium 100-octane fuel. To feed these foreign engines, standard Soviet domestic B-78 or 70-octane gasoline was an absolute impossibility. If flown on such low-grade fuels, the high-compression Allison V1710 engine of the P-39 Airacobra or the Rolls-Royce Merlin engine of the Spitfire would suffer catastrophic piston failure and cylinder block cracking within minutes of takeoff, effectively turning these sophisticated weapons into useless, grounded scrap metal. This was particularly critical for the Bell P-39 Airacobra, an aircraft that was largely rejected by the American and British Air Forces, but found its true calling in Soviet hands. Flown by elite Soviet aces like Alexander Pokryshkin, who scored the majority of his 59 victories in the Airacobra, the P-39 became a legendary symbol of Soviet tactical aviation. Pokryshkin and his comrades utilized the Airacobra in a highly aggressive, low to medium altitude role, capitalizing on its exceptional structural strength, powerful central cannon, and excellent visibility. Yet, this high-speed, high-G tactical combat required rapid, full-throttle engine responses. To maintain this extreme operational tempo, the Allison engines required a steady, clean supply of 100-octane fuel. The Soviet Union dedicated vast portions of its imported American fuel stocks exclusively to these Lend-Lease fighter regiments, ensuring that their elite squadrons always had access to the premium chemical energy required to maintain peak aerodynamic performance. The combat geography of the Eastern Front directly reflected this chemical logistics reality. During the savage air battles over the Kuban River in the spring of 1943, and later during the massive clash of armor at Kursk, Soviet Lend-Lease fighter divisions were strategically positioned close to the southern supply routes of the Persian corridor. This geographical proximity allowed for the rapid, direct transport of American octane shipments from Iranian ports across the Caspian Sea to frontline airfields. It was here, in the southern skies, that the Soviet Air Force broke the back of the Luftwaffe's tactical bomber fleet, a triumph made possible because their imported fighters were backed by a robust, high-performance fuel supply line. Without this American chemical foundation, the Soviet Union could never have successfully integrated these high-performance Western aircraft into their combat operations, leaving them unable to stem the tide of German air superiority and dramatically altering the course of the entire war on the ground. To truly appreciate the strategic weight of this chemical bottleneck, we must explore a terrifying and highly plausible counterfactual scenario. A coordinated German strategic effort that permanently strangles the Lend-Lease petroleum pipeline in late 1942. Imagine a reality where the catastrophic disaster of Convoy PQ-17 leads the British Admiralty to completely and permanently suspend the Arctic run, and where the German summer offensive of 1942, known as Case Blue, achieves its ultimate objectives. In this scenario, General Ewald von Kleist's 1st Panzer Army does not merely reach the outskirts of the Caucasus, but successfully crosses the mountain passes, severs the Trans-Iranian Railway at the Persian Gulf, and isolates the Soviet oil shipping lanes across the Caspian Sea. In a single stroke, over 90% of all high-octane fuel and alkylate imports to the Soviet Union are completely cut off, forcing the Soviet Union to rely entirely on its own primitive domestic refining capacity. The technical consequences of this chemical blockade would be immediate and catastrophic for the Soviet Air Force. Without American alkylates and additive packages to blend into their refinery runs, the production of high-grade aviation gasoline would instantly collapse to near zero. Soviet ground crews would be forced to fuel their frontline fighters with standard, low-octane domestic gasoline, a move that would require immediate and drastic mechanical detuning of every engine in service. To prevent the violent engine detonation that would otherwise shatter their cylinders, engineers would be forced to dial back supercharger boost pressures on the Klimov and Mikulin engines. By reducing boost limits, the Klimov M105 PF engine's output would fall by over 200 horsepower. The top speed of the standard Yakovlev Yak-9 and Lavochkin La-5 fighters would plunge by 40 to 50 kilometers per hour, while their climb times would double and their operating ceilings would drop by thousands of feet. Furthermore, the entire fleet of 18,000 Lend-Lease aircraft, including the elite P-39 Airacobra and Spitfire regiments, would be instantly grounded, transformed into heavy metal statues lining the edges of Soviet airfields. This drop in technical performance would completely reshape the tactical and strategic balance of power in the skies above Russia. The Luftwaffe, flying their highly refined Messerschmitts and Focke-Wulfs running on advanced synthetic aviation fuels, would re-establish a crushing, uncontested air superiority over the entire front. Soviet fighters, sluggish and unable to reach high combat altitudes, would be easily picked off by German interceptor squadrons. Without reliable Soviet fighter cover, the Red Army's ground attack aircraft, the Ilyushin Il-2 Sturmovik, would become easy prey for German fighter aces, making it impossible for the Soviets to provide tactical air support for their ground troops. Most decisively, the lack of air cover would paralyze the Soviet Red Army's offensive doctrine of deep battle. During the massive armored offensives of 1943 and 44, Soviet tank columns would be forced to advance under open skies, completely exposed to the lethal, coordinated attacks of German Junkers Ju-87 Stukas and Henschel Haas 129 tank killers. The great encirclements of the late war would remain unexecuted, and the Soviet advance would grind to a bloody, stagnant halt under the unopposed shadow of German wings, demonstrating that the chemical composition of fuel was the ultimate foundation upon which Soviet victory was built. The historical reality of the Second World War on the Eastern Front is often obscured by the monumental myths of self-sufficient patriotic production. Standard Soviet historiography and popular modern accounts alike tend to emphasize the isolated triumphs of Soviet design and the stoic endurance of the Soviet worker. We are left with the image of a nation that won the war purely through the brute force of its steel mills and the sheer volume of its assembly lines. Yet this narrative is an illusion that ignores the complex, delicate chemistry of modern industrial warfare. A tank is not merely a hunk of steel, it is a mechanical system that requires oil, grease, ball bearings, rubber tires, and high-frequency radios to function. An aircraft is not merely a collection of wings and engines, it is a high-altitude combustion chamber that is entirely dependent on the chemical purity of the fuel that ignites within its pistons. The thousands of T-34 tanks and Ilyushin Sturmovix that rolled out of Soviet factories were not independent achievements. They were the physical components of a grand transnational industrial machine that depended absolutely on the advanced chemical engineering of Western oil refineries. To sever this chemical connection is to realize that modern war is an intricate, interdependent web where the strength of the chain is decided entirely by its weakest, most microscopic link. The Soviet Union possessed the raw materials, the steel, the coal, and the human courage to fight the German invader, but they lacked the highly specialized chemical processes required to make those raw materials effective on a modern high-tech battlefield. The American catalytic cracking plants of the 1940s did not merely produce a liquid fuel, they manufactured the strategic oxygen that allowed the Soviet war machine to breathe. Without the steady, massive influx of American high-octane fuel, alkylates and chemical additives, the Soviet Union would have been forced to fight a 20th century industrial war with agricultural-grade energy, reducing their highly advanced aircraft and tanks to low-performance machines that would have been systematically annihilated by a chemically superior enemy. Ultimately, the lesson of the aviation fuel bottleneck on the Eastern Front is that modern victory is decided not in the physical clash of weapons, but in the invisible synergy of global logistics and advanced industrial chemistry. The heroism of the Soviet soldier and the tactical brilliance of their commanders were undeniable, but these human qualities were only made effective because they were backed by the unyielding, high-performance output of American chemical refineries. When we look back at the grand sweeps of the Red Army across Eastern Europe, we are looking at a triumph of metallurgical and chemical cooperation that transcended national borders. It is a reminder that in the crucible of total industrial war, the ultimate arbiter of destiny is often found not in the size of an army, but in the octane rating of its fuel, revealing that the silent, microscopic compounds of chemistry are the true, invisible pillars upon which the empires of the modern world are built.